Hello students, I am Tanzanudin and we are going to go with the sets part 3, and certain topics that we are going to cover today would be Venn diagram and then operation on sets, then we'll do some laws of algebra and then theorem on sets algebra, and lastly we'll be doing certain relations on number of elements in the sets. Alright, so these are the certain topics that we are going to cover in chapter sets. Okay. So to begin with, Venn diagrams. A scientist, a mathematician by the name John Venn, in collaboration with Euler, devised a method of operations of sets, and that method came to be known as Venn diagram. Okay, so what he did was he created certain diagrams through which set can be represented and their operations as well. So likewise I'll be going with operations together. Okay, so operations in set. So certain operations, for example, first union, okay, represented by a U. Alright, now I'll be collaborating Venn diagrams topic with operation in set, and you can understand clearly how a Venn diagram and operation of sets function. Simple? Alright, so to begin with, let's say to understand this operation union, we have a set A. Okay, let's say set A's element is 1, 2, 3, 4, 5. Clear? Similarly, we have set B. Let's say it has certain elements 3, 5, 6 and 7. Okay. Now looking at the structure of the sets A and B, we see certain common elements. The elements are 3 and 3, 5 and 5. Rest all are different, even though some elements are correlating. Alright. Now how do we represent a Venn diagram? Simple. In a Venn diagram, we have a universal set. If you remember what a universal set is, okay, it is represented by a square box. Simple. Now this is a universal set that contains all the set of A and B included. Alright. Now next step, what happens? We have to represent set A and set B within this universal set. Okay. So first thing, let's represent set A. Alright. This is how we are going to represent a set. Alright. Now this set A has certain elements which is in the set. So we'll be writing the elements in the set, but before writing, we see that certain elements of set A are also in the set B as well. So we will overlap the set A diagram with the set B diagram. Let's say this is set A and this is set B, and this whole square box is the universal set U. Simple. Now the elements that are same in the two sets will be written in a region where both the sets are overlapping. Is it clear? So what are the elements? 3 and 5, 3 and 5. So I'll be writing 3, 5 over here. Okay. Now what are left in set A? 1, 2 and 3. 3 done. 4. So 1, 2, 4. Okay. Simple. Next we have in B set, we have 3 and 5 what's been written. So 6 and 7. 6 and 7. Alright. Now universal set U shows us the set A and B all together. Now the one thing that we were talking about was the union. So how do we represent? We represent A union B. Simple. A union B, or it is also stated as A or B. Simple. In computer science, students always use OR symbol, and then we know that OR symbol represents as addition. Likewise, in this, union also represents addition. Addition in the sense, what happens is when two sets are undergoing union operation, what happens is the resultant would be the elements of A and elements of B all together. Alright, so A union B would be equal to a new set that would combine the elements of A and elements of B as well. So A union B would be 1, 2, 3, 4, 5, 6, 7. Simple. And in Venn diagram, if I represent A union B, it would be this whole part. This whole region would be the region of operation A union B. Simple. Okay. So all we needed to do was all the elements of A and all the elements of B all written together. But do remember, the elements do not repeat. The elements that are same will not be repeated. It will be written only once. Simple. Okay. Now this is called union. First operation. The second operation is intersection, and it is represented by inverted U. Simple. Now I've got a set A. Again, let's say it is set A has certain elements A, B, C and D. Okay. Similarly, set B has many elements C, D, E, F. Simple. Alright. Now what happens in intersection? Let's say we represent A intersection B is equal to. Alright. In union, what we did was we wrote all the elements together. Alright. Now opposite to this, in intersection, what we will do is we will write only the elements that are in both the sets. Simple. The elements that are both sets will be the set of intersection. Simple. So once again, same thing happens over here. What we see is set A, set B. Now I'll be writing the elements of set A and set B as we did earlier. In set A and set B, what are the elements that are repeated? C and D. Where do we write it? The overlapping region. Simple. What is left? A and B in set A, and CD being repeated, E and F in set B. Okay. Now A intersection B is equal to the elements that are in both the sets. That means the elements that are in the overlapping region of the Venn diagram. So this would be set C comma D. Simple. Okay. So to represent this set in the Venn diagram, the region would be this region. Simple. Okay. So this is your second operation, which is intersection. All right. Now for the third operation is known as difference between sets. Difference of the set. Difference of the sets. So let's say set A has certain elements 1, 2, 3, 4, 5, and then set B has few elements, let's say 3, 4, 5, 6, 7. All right. Now the difference in the set depends on which element is being written first, okay, or depends on which set is being written first. All right. For example, let's find the difference of set A minus B. All right. Now set A minus B would be the resultant set in which we will subtract all the elements that are in B as well. Okay. From where? From set A. Is it clear? All right. So to understand this, let's say set A minus B is equal to, in set A we have elements 1, 2, 3, 4 and 5. Similarly in set B, what are the correlating elements? The elements that have been repeated, 3, 4 and 5. So what we do is from set A, we will subtract or we will remove the elements that are in set B as well. So which elements are in B as well? 3, 4 and 5. 3, 4 and 5. Okay. Irrespective of what is left in B, we will only check what is left in A. 3, 4, 5 being removed, what is left? 1 and 2. Simple. So A minus B would be 1 and 2. Simple. All right. How do you represent it? Set A, set B. Simple. Set A has elements 1, 2, 3, 4, 5. 1, 2 being the only element that are in exclusively A. Okay. And 3, 4, 5 are the shared elements with B. 3, 4, 5 being written, 6 and 7 exclusive to B. Simple. All right. So A minus B, as I have told you, the answer is 1, 2. Clear? Okay. Now this answer is 1, 2. You can see clearly which region is 1, 2. So this region, the region that is exclusively to A and A only. All right. So this is difference of set. Now instead of writing A minus B, if I wrote B minus A, B minus A would be again 3, 4, 5 being repeated in A and B as well. We remove it. What is left? Only 6 and 7. Okay. Can you see the difference? So by writing B first, I'll be getting 6, 7. By writing A first, I'll be getting 1, 2. In each case, what we are getting? The exclusive part only. Exclusive to the first set. Exclusive to the first set. Okay. So B minus A is equal to which one? The set 6, 7. Okay. Now represent it in the diagram, which is this portion. Simple. All right. So this is the difference of the sets. So next we are going to talk about the fourth operation. The fourth operation is symmetric difference. So by symmetric difference, we represent it in the form of a triangle, okay, delta as we call it. So let's say set A is an element, set A has elements 1, 2, 3, 4, 5. Similarly, set B is another set with certain elements, say 2, 4, 5, 6, and let's say 7 as well. Okay. Now, if I need to find the symmetric difference between set A and set B, I'll be writing A delta B is equal to A minus B union B minus A. Alright, so from this equation I am telling you that the symmetric difference between two sets A and B is equal to A minus B union B minus A. So as you can see, mathematically or diagrammatically, we can represent it as a region that is exclusive to A minus B alone and then B minus A alone. And from the past question, difference between sets, we already know A minus B is the region that is only exclusive to A. Okay, and then union means to add up on top of that, okay, or this or that, any of the one. So B minus A would be the region that is exclusive to B set alone. Okay, set A and set B. So this shows that in symmetric difference, the region that we are getting is such a region that is excluding the overlapping region. Okay, so this region is being excluded, rest everything is included. So this is symmetric difference. For example, in case of this values, the elements, say set A is 1, 2, 3, 5. What is being repeated? 2 is being repeated, 4 is being repeated. Anything else? 5 is also repeated. So 1, 3 is exclusive to set A. Okay. 2, 4, 5 is the overlapping region. And then for set B, 2, 4, 5 is the overlapping region. What is left? 6, 7. 6 and 7 is left. So you can clearly see symmetric difference between A and B is equal to this region and this region excluding the central region. Is it clear? So the resultant set would be 1, 3, 6, 7. Clear? Okay. So in this way we have completed both the topics, which is Venn diagram and operation in sets. So you can clearly see why Venn diagram we are easily able to represent a union, intersection, okay, and certain operations as well. All right. So what are the operations that we did? We did union, we did intersection, and what was the symbol for union? U. What was symbol for intersection? Inverted U. And then we did difference. We also did symmetric difference. Delta. Okay, so these are the certain operations that we did. That being said, in case of intersection, not every sets would overlap. By that I mean, for example, I have a set A that has elements 1, 2, 3, and then set B that has elements say 4, 5. Clear? Now, if I draw a Venn diagram of intersection in this case, the diagram would be something like this. This is set A, this is set B. Okay? Set A has elements 1, 2, 3, and set B has elements 4, 5. Okay, and from here it is clear that there are no overlapping elements in both the sets. Alright, so in this case the intersection would be no intersection. Okay, so the resultant of the intersection of set A with set B would be a null set. Okay, now this symbol is a null set. Everyone remembers it. We talked about it earlier as well. Okay, so A intersection B would be a null set. Reason? There are no overlapping elements, and such elements or such sets in which the intersection is always a null set, such sets are called disjoint set. Okay, so based on the operation, we have another type of set which is known as disjoint set. Is it clear? Okay. Next we are going to do laws of algebra, but before that we missed out a small operation which is known as complement. Okay, what is a complement? Say we have a universal set U that has all the elements of set A and set B. Okay, so let's say set A is 1, 2, 3, 4. Okay, now I'm not writing set B because it is irrespective. You don't need to write the set B over here. What we are going to do is we are going to find the complement of A. So how do you represent the complement of A? This is how you write it. Okay, A complement. This means that the set A has been under the operation complement. Now what happens after this complement operation is operated? You are going to get all the values that are left after the set A has been subtracted from universal set U. Okay, so universal set U is 1, 2, 3, 4, 5, 6, 7. Set A is 1, 2, 3, 4. After removing set A from set U, what is left? We are left with 5, 6, 7. 5, 6, 7. So this is the complement of A. Simple. All you need to do is remove all the elements of A from the universal set. Alright. Say universal set U is X belongs to real numbers. Okay. All the real numbers are inclusive in universal set. Okay. So let's say few subsets of universal set real numbers. We all know Z is 1, N is 1. By Z, what does Z mean? Z is all the integers. In mathematics, we represent integers by capital Z. Similarly, N is for natural numbers. And then we have Q. By Q, we mean rational numbers. So if Q is for rational numbers, in that case your T would be irrational number, which is Q complement. If you understand the concept of rational number, your T would be Q complement. That means T would be irrational numbers. Okay, so these are certain symbols that we use in mathematics daily. Z for integers, N for natural numbers, Q for rational numbers, and T is irrational numbers. Or using this operation complement, we have Q complement is irrational number. Alright, all the numbers that are not rational number would be irrational number. Simple. Then we have last C as well, which is complex number. If you do not know what a complex number is, we'll be talking about it later in class 11th. Okay. So the next topic that we are going to study today is laws of algebra. Of sets. Okay. So first law is called Idempotent Law. Simple. In idempotent law, we all know that when A is operated by union with itself, we'll be getting A again. Alright, through Venn diagram we can clearly know that all the elements when correlating, when same, when operated by union will give me the same set. Simple. Similarly, for intersection as well, A intersection A would again give me A. Okay, so in case of union and intersection with the same set itself would give me the same set. Okay, next we have identity law. So A union with a null set would give me A. Okay, when A is a set that is being operated by union with a null set, the resultant would be A itself. Similarly, for intersection, A when intersected with a universal set would give me A. Simple. Okay, all the elements would be inclusive in the universal set, that is clear. So when the intersection of A is done with the universal set U, you will be getting A again. Simple. We have third, commutative law. After identity law, we have next commutative law. By commutative law, everybody knows that A union B equals to B union A. There is no change over here. It remains same. Similarly, A intersection B would be B intersection A. Same thing happens again. Okay, so this is commutative. All the operations on sets, okay, is commutative in nature. Fourth, we have associative law. Okay, and this law, as the name suggests, it's about associating. So if we write A union B union C, so this can be written as A union B union C. Okay, so it is clear, as you know, the bracket. Okay, when the operation is done, we follow the bracket first. So first union of A and B, then union with C is same as first union of B and C, then with A. Now same thing happens with intersection as well. Okay, A intersection B intersection C would be same as A intersection B intersection C. Simple. Okay, now law number 5, we have distributive law. Okay, so as the name suggests, we have to show the distributive nature of the operations of set. Okay, so A intersection with A union B, this can be written as, or let's change it, let's write A intersection B union C. Okay, that would be better. So A intersection B, I am distributing. Okay, what is in the center? Union bracket A intersection C. Clear? Same thing happens with the union. A union B intersection C. This would be A union B. What is in the center? Intersection A union C. Clear? Okay, so these are the 5 laws. These are the 5 laws on the operations of set. There's one more law by the name of De Morgan's law. So De Morgan's law states that A union B whole complement is equal to A complement intersection of B complement. Similarly, for intersection A intersection B whole complement. Now in this case, what is happening? First you are finding the union of A and B, and then you are operating a complement on whole operation. Okay, so after union, a complement. Alright, now this is equal to A complement intersection of B complement. The union turns into intersection and the complement is distributed to A and B. Same thing in intersection, we have A complement union B complement. Okay, now this De Morgan's law, it's a very familiar law for the computer science students. They may know what a De Morgan's law is. So this is what De Morgan's law is, okay, which is quite helpful in certain provings. Okay, next we are going to solve a question based on the algebra of sets. Okay, so the question goes like, let A and B be any two sets, and if A intersection X equals to B intersection X is equal to a null set phi, and A union X and B union X for some set X, then you have to prove that set A is equal to set B. Okay, so in this question we are going to use certain properties like we just studied about idempotent, okay, identity, and then associative, commutative, and distributive as well. So these properties are going to be used in this question. All right, so to begin with, we'll take this equation, given equation, that states that A union X is equal to B union X. Okay, now this equation has been given in the question. Okay, so first step, what we are going to do is we are going to use A intersection on both the sides. All right, now when A is intersected with A union X, so what is happening is, if an equal is added on any given equal, the resultant would again be an equal. So therefore this equation does not change. Okay, this is an equal, and then equal operation has been operated in both the cases. Then left hand side equals to right hand side. So next step would be opening the brackets. Okay, by opening the brackets, what we are going to operate is we are going to operate a distributive law. So this would become A intersection A, this into this, and then this into this. What is in the center? It is union. What is A intersection X? Okay, now this intersection has been taken knowingly. We will later know why it has been taken. Okay, similarly, A intersection B union with A intersection X. Okay, so this is going to be your first step. So next step, we have A intersection A. So what is the value of A intersection A? Idempotent law. A intersection A is A itself. Okay, now union with A intersection X. So from above given values, what is the value of A intersection X? As you can see over here, A intersection X is a null set phi. Simple. So A union A intersection X being null set phi equals to A intersection B. Okay, as it is, I won't be changing it. A intersection B. Now union with A intersection X. Again, the value of A intersection X is null set. Okay, so from above values we are putting the null sets. After putting the null set, again let's get back to identity law. Okay, A union with null set would give me A again. Okay, now if I place union over here, it would create a problem. Okay, so therefore intersection has been used. So A union with a null set would give me A again, and then same thing over here, A intersection B union with a null set would again be A intersection B. Clear? Now let this be my first equation. Simple. Now for the second part, if I am able to prove that B is also equal to A intersection B, so from equation 1 and equation 2, I can prove that A equals to B. So what we'll do is, we'll prove A intersection B is equal to B. Alright. So to prove that, again, we'll be going with the same equation. A union X is equal to B union X. Okay. So A union X equals to B union X. Okay. So in this case, what we did was we used intersection of A. So over here it would be B intersection. B intersection B union of X. Simple. Now if we use distributive law, what will we be getting? B intersection A union with B intersection X. Okay. Now this would be equal to B intersection B union with B intersection X. Alright. From above, we all know the value of B intersection X. B intersection X is equal to null set. Okay. So this would be equal to B intersection A union with the null set equals to, what is B intersection B? Idempotent law. It would be B union with B intersection X is a null set, phi. Okay. Now again, union with the null set, it will again be B intersection A equals to B. Alright. Clear? Now using commutative law, B intersection A can also be written as A intersection B. This is my second equation. Alright. So now it is clear already that section 1 and section 2 are equal. How? A intersection B equals to A intersection B equals to B. So we'll be writing from 1 and 2, we have A intersection B equals to A equals to B, which is what is required to be proved. Hence, A equals to B has been proved. Simple. So next we are going to study about certain theorems based on the operations and algebras of the set. Okay. So these are certain operations that are useful in certain questions. Okay, mostly complex question based on IITs. Okay, so formulas are such that you have to use them and then solve them certain questions. All right. So A minus B would be A intersection B complement. Similarly, B minus A equals to B intersection A complement. Okay. Now I'm not going into the details about how this has been coming about and the provings as well. I'll do some provings, not every one of them. Okay. So that would be your job if you understood, as good, fine. Otherwise you need to find about it. Okay. And then you try to search about the derivations, how they come about. Okay. I'll do few of them though. All right. So A minus B equals to A. This implies that A intersection of B is a null set. Similarly, A minus B union B equals to A union B. And then A minus B when intersection with B will give me a null set. So certain theorems are very important. They come about again and again in every questions. Okay. All right. Something like this. All right. And then fourth is, if A is a subset of B, then that means that B complement is also a subset of A complement. Okay. A minus B when union with B minus A would give me A union B minus A intersection B. All right. Now certain more important theorems. These are general theorems. Based on these theorems, there are a few more theorems. These theorems are very important as well. A minus B intersection C equals to A minus B union with A minus C. Similarly, A minus B union C equals to A minus B intersection with A minus C. And then A intersection B minus C equals to A intersection B minus A intersection C. And then A intersection B delta C. Delta means symmetric difference, as you know already, equals to A intersection B delta A intersection C. All right. So let's do proving of one or two theorems. Okay. let's say we'll do this theorem and this theorem. Okay. Rest theorem are general theorems, and based on these general theorems, we have greater theorems. These theorems are very important as well. All right. So we are going to do the proving of this theorem. Even though there are lots of theorems, all the proving would not be possible because of shortage of time. So we'll just do few of them. Okay. The method would be same in each cases. Okay. Most of them will be following the same cases. All right. So to begin with, we have A minus B union C equals to A minus B intersection with A minus C. Okay. Now let's say X is an arbitrary element such that X belongs to this set. Okay. The set is A minus B intersection with A minus C. All right. Now, X being an arbitrary element that belongs to this set, so by the rule of difference and operations of set, we can write that X belongs to A minus B intersection A minus C. This can be further broken down into X belongs to A and X does not belong to B. As you can see clearly over here, X belongs to A minus B. Minus B means the B elements are being removed from set. Okay. So since X belongs to A and X does not belong to B, okay, this is my first bracket, okay, this part. All right. Now intersection and again, X belongs to A and X does not belong to C. All right. Now I'm breaking this into this step by step. Okay. And it's clear. You can see it. All right. Now since X belongs to A and X does not belong to B, that is clear. What we will do is we will take these two common. All right. Now X belongs to A and taking this common, what is left? X does not belong to B and X does not belong to C. Clear? Now since X is an element such that it does not belong to B and it does not belong to C as well, therefore we might as well combine this together in a statement. Okay. So how do you combine it? X belongs to A and X does not belong to B union C. I'll take these two sets B and C together since X does not belong to both of them. Okay. So that being said, we can write X belongs to A but it does not belong to B union C minus B union C. All right. Clear? So from this line, we can see clearly that X is an arbitrary element of this set, but this element is also an element of A minus B union C through this process. Okay. Now since X is an element of this as well, therefore we can write that A minus B intersection with A minus C is a subset of A minus B union C. Clear? All right. Now, this is the first step where I've been able to prove that this set is a subset of this set. So, to prove any two sets equal, all right, And this implies for any type of question, same as this. Okay. So to prove any set to be equal, what we need to do is we need to prove two things. All right. This is a method. We need to prove two things. First proof is to prove that given set A is a subset of B and set B is a subset of A. If you are able to prove these two things, then this would imply that a set A equals to set B. Okay? Clear? Now, in this question, instead of set A, we have this whole set. A minus B union C. And instead of set B, I have this whole set which is A minus B intersection A minus C. Now, if I am able to prove this is a subset of this, and later on again, this is a subset of this. So that would imply that these two are equal. Okay. So this theorem is being used in this question. Simple. Okay. So my first job was to prove that this is a subset of this, which has been done. Now this is my equation number 1. Okay. Now for equation number 1, A minus B intersection A minus C is a subset of A minus B union C. Similarly, through this method, we'll be proving that A minus B union C would be a subset of A minus B intersection A minus C. Okay. So to begin that, now instead of taking an arbitrary element X, I'll be taking arbitrary element Y. And this Y would belong to A minus B union C. Okay. Simple. Now let's say Y belongs to A minus B union C. Okay. So as we did earlier, it would be same over here. Y belongs to A and Y does not belong to B union C. Alright. Again, same thing happens here. Y belongs to A and Y does not belong to B and Y does not belong to C. Okay. Now if you open the brackets, what we'll get? Y belongs to A and Y does not belong to B and Y belongs to A and Y does not belong to C. Okay, simple. So if you write it mathematically, okay, by the rules, so we have Y belongs to A minus B and Y belongs to A minus C. Okay. Clear? So joining this up, we have Y belongs to A minus B intersection A minus C. Simple. Now Y is an arbitrary element belonging to A minus B union C, but it is also an element of A minus B intersection A minus C. Okay. So from here we can say that A minus B intersection with A minus C is a subset of sorry. So instead of writing this, I'll be writing, where did we begin from? We began from A minus B union C. So we can write A minus B union C is a subset of A minus B intersection of A minus C. Okay, now this is equation number 2. Clear? Now we can see clearly that from equation number 1, what has been proved is A minus B intersection A minus C is a subset of A minus B union C. And from equation number 2, we reciprocate it. A minus B union C is a subset of A minus B intersection A minus C. So these two equations are enough, and then by using this theorem that states that A is a subset of B, B is a subset of A, this implies that set A and set B are equal. So that using the theorem, we can say using the theorem, we can say that A minus B intersection A minus C equals to A minus B union C. Okay. So this is a method of proving the given theorem, which is slightly abstract in nature. Okay, even though this is the way how it is proved. Okay, and likewise every other theorem is also proved in this format as well. Okay, so using the operation of symmetric difference, we are going to solve the question. So let's take the left hand side first. LHS is equal to A intersection B symmetric difference C. So it will be written as A intersection B minus C, okay, union C minus B closed. Okay, clear? Now using distributive property, we can write A intersection B minus C union A intersection C minus B. Clear? This is the distributive property. Again, further distributing it, A intersection B minus A intersection C union with A intersection C minus A intersection B. Alright. Now you can see clearly A intersection B and A intersection B is over here. Similarly, A intersection C and A intersection C. Okay. Now if you place it as X and this is X and this is Y and this is Y, so you can see clearly that X minus Y union Y minus X is equal to X symmetric difference Y. Okay. So same thing we are going to do over here. Instead of X, we have A intersection B. Instead of Y, we have A intersection C. So this would be A intersection B symmetric difference with A intersection C, which is equal to RHS, hence proved. Okay, simple.